Today's lesson is on proving theorems. It's going to be a 3-day lesson, so this is day 1. Before we go forward, let's go back a little bit. It says the definition of a midpoint, which we've done before, but it's the point that divides the segment into two congruent segments. So if we look at our diagram, if I tell you that E is the midpoint, then what that means is segment DE is congruent to segment EF. We can also say that DE is also equal to EF. We're going to use the definition of midpoint to prove that segment AM is equal to half of segment AB and segment MB is equal to half of AB. So the first part we'll write is the given. M is the midpoint of segment AB. Now because of that, we know that our next step is going to be this. That means that segment AM is congruent to segment MB. And because that's true, things that are congruent are also equal, so we know that AM is equal to MB. And the reason we can say that is because of the definition of a midpoint. Now again, in a proof, I can pull that from the step before, step 1. Okay, so in our next step, the other thing I know is in looking at my diagram, I know that segment AM plus segment MB is equal to segment AB, and that's because of segment addition postulate. So I'm going to write that. So I have AM plus MB is equal to AB. Two small pieces equal the big piece, so that's segment addition postulate. Okay, looking at our diagram, that's pretty much all we can conclude from that. I don't have a specific measurement, but if I look above in my proof, there's a couple things I can do here. So in looking in the steps above, I have AM is the same as MB. I said that right there. So I can replace that. I have AM, and instead of writing MB, I'm going to actually write AM again, is equal to AB. Now when I rewrite that, AM is the same. So I have two of them. 2 times AM is equal to AB. And what I did there was I actually substituted. So I have substitution, property of equality. And what I did was I used steps 2 and 3, and I kind of moved things around. And when you're moving things around in geometry, you're substituting. Okay, and looking at my next step, so I'm trying to get to, again, my proof. So I have AM is equal to 1/2 of AB. So if I'm looking at step 4, what I can do is if I actually divide both sides by 2, that gives me AM is equal to 1/2 AB, which is actually what I'm trying to do up in my proof statement, which I was given. So what I did there is I divided both sides by 2, so it's division, property of equality. Now again, I'm kind of finishing up my last step. I took care of the one proof. I need to look at the other proof now. This MB is equal to 1/2 AB. Well, up here in step 2, I said that AM is the same as MB. So I can actually replace that. So I can say MB is equal to 1/2 of AB. And that is because of the substitution property of equality. Now what we just did is we proved the midpoint theorem. So we can now use the midpoint theorem in proofs in the future. Remember that a postulate is something we accept without proof, but a theorem is something that we can prove if we want to. So since we just proved the midpoint theorem, here's what it states. And looking at the diagram, if M is the midpoint of AB, so here M is the midpoint, then I know that AM is equal to 1/2 of AB. So the small part is equal to 1/2 of the big part. And MB is also equal to 1/2 of AB. That's different from the definition of midpoint. So remember, the definition of midpoint says that the point that divides a segment into two congruent segments. So that definitely says different things. So that's saying that, again, that AM is congruent to MB. And that therefore AM is also equal to MB. So in the midpoint theorem, that's talking about one of the smaller segments in relationship to the bigger segment. And in the definition of the midpoint, we're just comparing the two smaller segments, saying that they're congruent or equal. And looking at the angle bisector theorem, we could prove this if we wanted to, since it's a theorem, but the proof would look very similar to the midpoint theorem. So it says if ray BX, remember that a ray is the bisector of an angle, if ray BX is the bisector of angle ABC, then the measure of angle ABX, right here, is equal to half, again, of the big angle ABC. And we could say the same thing holds true for the other angle. The measure of angle XBC, this one here, is equal to half of the bigger angle. So that's the angle bisector theorem. So we can now use that in a proof. Again, if we compare that to the definition of the angle bisector, the definition of angle bisector says the ray that divides the angle into two congruent adjacent angles. So again, what we're saying there is I'm saying angle ABX is congruent to angle XBC. So in comparison, if I'm looking at the angle bisector theorem, I'm talking about one of the smaller angles in comparison to the big angle. And in the definition of an angle bisector, I'm talking about the two smaller angles, the fact that they are congruent. That's their relationship.